Hello, everybody. Thanks for joining the podcast. My name is Ivan Yimshikov. I'm a postdoc in Max Planck Institute for Mathematics and the Sciences. And today we have Jürgen Jost, who is the director of the very same institute. Hello, Jürgen, and thanks for joining us.
Well, with great pleasure.
So last year, you gave a lecture on your scientific career. And you started this lecture with the episode of how you became a mathematician. That, like, your origin story, let's say. And I thought it's a very interesting story because there is a wide perception that people who do mathematics do it like you're born mathematician, you stay a mathematician all your life, and they're just some very, very like not people-y people, let's say. They are very separate, and that this basically they just go in one straight line. But your origin story is quite more complicated and interesting. Can you kind of tell us how you became a mathematician?
Yes, I certainly did not go in a straight line. In high school, I was interested in many things. So the subject that fascinated me most and I was best in was classical Greek. But my Greek teacher, of course, told me there's no future in that. And mathematics was...
All of them were dead.
Yeah, well, mathematics was relatively easy. And as a high school student, of course, you're often quite respectless. So I was not very respectful towards my mathematics teacher.
Okay, so you didn't. So it was easy and you thought it's because of the teacher, basically, or like.
Well, I mean, my mathematics teacher was not such a good teacher, and so I quickly felt that I was superior to him in my mathematical understanding. So I also corrected him often, and I worked with my classmates to get them through the exams and all that. And then, since I was interested in many things, finally I thought that doing mathematics would be rather general study, so that then with sound training in mathematics, I could also do many things afterwards. And so I also studied other subjects. I studied some physics, some economics, and some philosophy.
Yeah, you also mentioned that somehow philosophy seminars were too crowded. So
right.
Okay.
They were too crowded, and also the level there of the students and of the professors was not as high as in those other fields. It's, for example, some very good economics professors.
Okay. And also you mentioned that you came back from the army and you hated the experience of being told what to do. And
yes, precisely. Then, and in the army, as you said, I didn't like that other people could give me commands and I had to obey them. I thought I have to do something with my life where nobody can give me commands. And then from the very first day of my studies, I worked quite hard, and that then, of course, paid off. And so I advanced quite quickly, and I could also do a very quick PhD in mathematics.
Yeah, but like this part, so in science, there are different types of scientific advisors, let's put it this way. And there are some who give commands to their PhD students. So how these things work out, like in science? Do you think it's a good tendency, let's say, in science?
It depends. I mean, that was a reason why, for instance, I did mathematics rather than economics, because in mathematics you don't have that culture of the professor giving commands to the students. So the good students have much freedom to develop their own ideas. And of course, every advisor who has a good student has to face a prospect that after a year or two, the student will do much better things than this advisor himself did in his entire career. So people are a little careful there towards students. And in particular, in mathematics, you can get quite quickly towards the international level of research. There's not that much material that you have to absorb and learn. You have to be trained in a particular way of thinking. In other fields, you have to absorb a lot of tradition, a lot of material, and the time that it takes in order to become really a top international researcher or the path it takes towards that is much more winding.
So this structure is needed because the fields imply that you have to absorb more information and tradition. This is why, for example, economics has this structure.
Yes.
Okay. Yeah. That's interesting. But at the same time, technically, mathematics is much longer intellectual tradition than economics.
That is true.
So
yeah.
how did it happen in a sense that? What's so peculiar about mathematics that despite that it's probably one of the oldest intellectual systematic activities that humans do, you still can get an international level in a given field relatively fast?
Yeah, mathematics is still developing and expanding, and so new problems emerge. In economics, for instance, they have a much more constrained subject. Yeah, but mathematics and physics, computer science are relatively similar in that regard. That they're open and new problems emerge. And when a new problem comes up, of course, you have to use your training, your ability to systematically and logically think through problems. But then, when you have that ability, you can start relatively fresh.
Okay, so about this thinking possibility, thinking through problems. So one of the reasons I was like, I also had trouble choosing what I should do in life, as you can clearly tell. I still have it. but one of the arguments why I decided that I wanted to do something mathematical was that it gives you some structure of thinking about the world.
Yeah.
And it's hard to characterize it, like what is mathematical thinking, what is not. But it would be interesting to hear how you think about it. Like what are specifics? What are the aspects of mathematical thinking that make it so useful, even outside of mathematics? Because a lot of people learn that are good in mathematics in the school or in the university, then kind of show their abilities elsewhere and always say that helped me, right? So there seems to be something right about the way it structures the mind.
Well, I mean, certainly it's not the only approach that can be successful, but maybe from a very general perspective. In philosophy and the humanities, people think in terms of concepts. In physics, you have to think in terms of models, but in mathematics, you have to think in terms of structures. Mm-hmm. You have to identify structures. And you have, whenever you are faced with a particular problem, you have to learn how to quickly understand the abstract structure behind that, regardless of where the problem comes from and how it is implemented and what the details are.
Okay, and this capability, it's I think I was reading the book by some book on fractals. I'm not sure if it was the original Mandelbrot book or something else. And the author mentioned that when you learn what is a fractal, you start to see fractal structures everywhere. And you cannot unsee it, like in a sense that this is knowledge that you just get and it stays with you. Like you start looking at a sunflower and you never see the sunflower you saw when you were a kid. You never see this just irregular brown center of the sunflower. You always know that it's a fractal. So it's something like this. It's mathematics in general like this.
Well, that is somehow other a danger of mathematical thinking, that once you see one particular, have identified and learned one particular structure, then you see nothing else. So you need to keep up your flexibility to also identify and see new structures all the time.
But so people who do fractals, that's the problem. They are not flexible enough.
Yeah, but also other people, once they have developed a particular method or so in statistics or numerics or so, then for the rest of their lives, they want to find applications for that method and always try to see structures to which that particular method fits.
But isn't this how a vast majority of academic careers work? The person
unfortunately, yes. Yeah.
Okay. So what you mentioned, unfortunately. So why do you find it unfortunate?
Well, I mean, important progress in science, of course, comes often from the identification of new structures and from the openness towards understanding things that have not been understood before, and where the existing structures might not really fit.
Okay, and so if the real progress comes from there, why majority of career scientists don't go in this direction?
Well, this is difficult.
Well,
Yeah,
but nobody told them that this. I'm sure that most of the people who choose science for their career are not afraid of difficulties. It's not an easy
They're not
endeavor.
afraid of difficulties, but once they've mastered some difficult structure, it's understandable that they want to capitalize on that.
Okay.
Yeah, that is the old dilemma between exploration and exploitation.
Okay, so we as a species tend to exploit things we found anyway, and this is kind of replicating all over the fields, no matter the field, whether it's science or business or what.
Yeah, that is what often happens. That's not necessarily bad, because if you have a knowledge about a particular structure like a fractal and so, then if you see fractals where they really are, but where other people have not seen them before, that can of course be useful. The danger rather arises when you are confronted with a structure that might not succumb to this thinking in terms of fractals or whatever structures you have already learned and developed.
But I think, for example, this particular mathematics is a fascinating mathematics, but it was created for some very practical reasons. And actually, for computer graphics, for example, fractal structures played a huge role because they're relatively easy to describe a spanning rule that then creates fascinating, beautiful images. I don't know, but there are other examples, like, for example, the Brownian motion looks very, very much like traveling across some rocky skyline, right? Because it's self-replicating in a sense. If you zoom into Brownian motion, it looks like you fly over some skyline. So this is beautiful mathematics, but it's very relatable because it finds an application. A lot of mathematics doesn't find an application, or it seems so for a lot of people. So what is this balance, and why people think that in mathematics it's very skewed towards non-applicable things?
Well, it's a delicate and fragile balance. I mean, many mathematical structures have been developed without any regard towards applications, but then when they're really good and deep and profound mathematical structures, they often find some very unexpected applications later on. So, for example, Riemannian geometry was developed just from the desire to develop a new mathematical understanding of space, but then later on it was a mathematical basis not only for the general theory of relativity, but also for much of quantum field theory or in other fields of physics, nonlinear elasticity theory, and so on.
Yeah, or like Galois developed some things that then turned out to be very useful for fluid models and for aerodynamics, for example.
Yeah, also for cryptography. Yes. So many results in number theory, which traditionally is considered to be the field most remote from applications, now find applications in cryptography, for instance, or in other parts of computer science.
But sometimes there are several hundred years between the mathematical result and application. Well, at least 100 years may pass between the two, right? So
that is true, but probably the time will get ever shorter, because mathematics now is expanding in data science, and you need to find and explore structure in data, and you don't know what the structures are. So it's very good that we have a very rich repertoire of mathematical structures which may guide our thinking. Of course, we cannot expect that all mathematical structures will find applications, but we need to have the freedom to develop enough structures so that some of them will find applications, although we cannot predict which ones.
Mm-hmm. But like I want to talk about data science as well at some point. But before that, I want to come back to this. So you mentioned that in mathematics, it's a very long line of human endeavor, and we always find something new to do about it. But it's also very, coming back to your favorite Greeks, it's very Platonistic in a sense. It's very close to what Plato describes as the actual idea, in a sense that it's sort of a form of very abstract truth that can be found based from very, very basic principles, right? So how, like, do you see any connection, or maybe there's some other way to think about it, like why and the connection between this general potential of mathematics and this abstract level of it, because it's probably one of the most abstract ways of thinking, let's say.
Yeah, there are several aspects in this. First of all, I agree that mathematics is about the oldest science, perhaps together with astronomy. We have a tradition of 2.5 millennia. Of course, then it is quite developed. And so it's not surprising that you cannot so easily explain mathematical results to a general audience. Then, of course, as you also said, mathematics was already tried to be philosophically conceptualized by Plato and others. But of course, one needs to be a little careful whether the picture of just discovering abstract pre-existing structures that exist independently and outside of the human mind really is the appropriate one. There's also a constructive aspect of mathematics.
Can you elaborate on that? Because do I understand you correctly? You're saying that the way our brain works on a more or less biological, maybe even level, makes us discover certain mathematics. Could one say it this way?
In some sense, yes, but we should not underestimate the constructive aspect of the brain. The brain is not just recording and structuring what is outside there. It actively creates structures with which to interpret the outside world. That is a Kantian approach in philosophy, and maybe that is in the end more appropriate than the Platonistic one.
Mm-hmm. So we actively create certain abstract concepts that help us internalize external information.
Yeah, to make sense of the world, yeah.
But the question is the mechanism that allows us to create these concepts. Let's say, what are what is it rooted in, right? Because we don't see, or we cannot, at least so far, measure the ability to construct these concepts outside of human species, let's say.
Of course.
Even within human species, we are not sure.
Yeah, but for instance, for a long time it was thought that Euclidean geometry is necessary because it is in some sense abstracted from our daily experience of space. So that is how we construct and conceptualize space. But then mathematicians in the 19th century already discovered that other types of geometries are possible. And then, of course, these other types of geometry were also found in nature, or were used to interpret things that are found in nature, in particular hyperbolic geometry.
But this fact that we perceive the world through our mind, and there's clear some inference, this is in itself, like, can mathematics help us, let's say, be less anthropocentric in our perspective, or not? Or is it all constructive? Is it all basically because if you take this Kantian approach to the world, then basically we can never leave this basic mechanism that allows us constructing structures.
Yeah,
we are confined to it in some sense.
Yes, but perhaps there's some kind of resonance. Of course, in order to be understandable, the world needs to be structured in some way. It cannot just be a random collection of data and events, otherwise we could not live in the world. But on the other hand, the structure is hidden. It's not so transparent, so we need to think about it and try to invent and try out different ones until we find one that best matches what we see in the world.
Yeah, that is where what I'm trying to explain is that if that's the case, we always have some margin of error,
Yeah.
And so we kind of have the spectrum of structures that we developed through mathematics. And then we see how the structures that we kind of have as these Lego cubes, how well they fit the actual analog reality, let's say, right? But if the set of structures is constructive, then there's no any guarantee that it is in any way, shape, or form correct, right? It's just like we constructed it because we are we, and then we just found a structure that fits better out of the limited space that we constructed. So that's the paradox I wanted to unpack. All right. So what can we do something about that? Can mathematics help us think about that?
Well, that is a challenge to identify the types of structures that we really find in the data and in the outside world. And I think that is the most important fundamental question of current data science.
This is where I was going. Because now we got... I've been thinking about modeling recently in a way that theoreticians will kill me for now. But I'll tell... So if you have limited memory and limited computational capacity, you need information compression.
Yes.
And modeling is essentially that. You look at a very complex word and you compress it into a model that fits into your brain. Now, if you have unlimited memory and computational capacity, the value of model becomes much harder to determine.
Yeah. Then you don't need a model, and then there would be no scientific progress.
Well, that's just an interesting question. Do we go in this? We do seem to go in the direction of memory is clearly not a problem anymore. For a vast majority of the problems, we can store as much information about them as we want. Computation is still a problem, but there are some people who talk about quantum computers, and they claim that once we get there, then computation won't be a problem. Then does it mean that that's where science ends, or?
No, that is also not the task of science. So, for instance, a map with a scale of 1 to 1 is completely useless. Yeah,
that's true.
Yeah, so you need to be able to identify the important aspects and separate them from the non-important ones by reducing the amount of data and find some way to extract what is regular and separate it from what is random. If you have unlimited capacities and you record everything that is random, but that doesn't help you.
Yeah. So the randomness is that's one of the aspects that data science claims to deal relatively well with, right? So randomness is something that you want to filter. Yeah. That's clear. But then coming back to this fit of structure to the reality, and the question of whether the structure that fits best out of the structures within the class that we possess is the optimal structure, and how we can differentiate between something that's constructive because it comes from our brain and something that's, I don't know how one calls the other type of structures, but let's say the structure that exists outside of it. Is there some way to think about it?
Well, let's come back to this data science or machine learning aspects. So far, the successful methods there do make certain abstract structural assumptions. So manifold learning assumes that the data sit on a low-dimensional but smooth manifold that can, of course, stretch in many directions in the ambient space. Compressed sensing assumes that you have only very few sources, and so on, or that you have certain symmetries and regularities there. If these assumptions are satisfied, then the methods work quite well. But when the assumptions are not satisfied, then they miserably fail. So the question is, what kind of structures or assumptions we should use as our kind of priors in the methods that we develop, that then can be confirmed in the data and that then reveal the structure in the data, and how to identify them then. And that is an abstract problem. So in order to deal with that, mathematics needs to be lifted to a probably higher level of abstraction.
in like what could be a path to go in this direction? I think this sounds very interesting, but it's very hard even to find an example of a model or an example of a problem in this direction that could move us.
Well, I mean, in the history of mathematics, always advances were made by looking at things from a more abstract perspective. And in particular, fields like number theory and geometry were unified by developing a perspective that encompasses both. And so, on one hand, mathematics is the science of particular structures, but it should move more and more towards the general science of structure, whatever the structure is.
Mm-hmm. So if we think about this let's say model fitting reality problem from this aspect, that what that would mean is that we have an agent, let's say, which is us, with available set of models.
That is a typical picture, that the agent has a set of models and then he or she tries out the models that are available and see which one fits.
But right. So what would be the more abstract way to look at this?
Yeah, well, to have a general science of models, to see what models could in principle be available and how to identify, without trying out many single ones, what model class would best fit the data.
So basically we remove the agent altogether and we think about a space of data?
The agent has to operate at a more abstract level. You don't want to have a statistician coming with his R package that he or she has developed over 20 years and then see whether that fits, or the numerical analyst that has developed, for instance, a very clever multi-grid technique and then
my point is that like how we can formulate this from the formal perspective is that we just have, let's say, we have some ground reality, some observable data, and then we have a class or some family of models. So we need to define some either space or some other structure that describes continuity or multiplicity of models, and then we need to think about it in context of how we navigate this space or some multitude of models with respect to the data available, right? So how can we steward our movement in this? I'm using geometric analogies because there's two ways to think, either in pictures or in words. And to think in words about this kind of things, it's getting hard. So geometric things come to mind. So that's one of the ways to look at it, right? That's actually an interesting. I think this is a good topic for a PhD, or maybe 10 PhDs. I don't know.
I mean, in that regard, it was one of the most important advances in mathematics when people systematically started to think about symmetries. Was the development of Lie groups, which incidentally took place here in Leipzig by Sophus Lie. Yeah. And that was a major step that then later helped physicists also to order the elementary particles in terms of their symmetries. And so therefore we need to think abstractly about such issues as symmetry and regularity and so on, perhaps even at a higher level that has not yet been conceived than has been done so far.
Yeah, but symmetry is also an example that I think a lot of people easily understand, that we see symmetrical things all the time. And then symmetry is also quite nice regarding this aspect of noise and model, because we think that human faces are symmetric, but they are actually not, right? This is a very interesting fact, that it's an example of this constructive nature of models, that we have constructed by our brain certain concept of symmetry, and then we simplify things around us with it.
Of course, I mean, that is the relation between what I call external complexity, what you see in the data, and the internal complexity, how you model it. And so the internal complexity, of course, should try to simplify things. And symmetries, of course, help you a lot because you just need to have some part, and then the rest can be reconstructed by applying the operation of the symmetry group, as in the Gestalt rules in psychology, for instance. And all the rest then is discarded as noise.
Yeah.
That is a basic aspect, but of course, often for finer understanding, the basic symmetry, maybe the left-right symmetry is not yet entirely sufficient, and so you need to look at certain finer details without getting overwhelmed by all the amount of details.
Yeah, so this is another thing. So you do also a lot, and you think a lot about neuroscience, mathematical neuroscience, for example. And one of the things that we discussed at some point was how perception works. That perception is essentially filtering.
But an active filter.
Yes, it's attention and filtering, right? So some combination of the two.
Yeah, not only, but for perception, you also have certain frames or whatever schemes in your mind that then get activated, and then the system has to check whether these frames or schemes are confirmed or whether they have to be abandoned. And only if a resonance sets in between some abstract scheme or frame in your brain and the data, then you feel that you have recognized things, and then they become conscious. Actually, that is how.
But that's once again, it's this aspect of constructiveness of this model. So at some point, like now, for example, cognitive biologists talk that nature and nurture are 50-50 in some sense.
Yeah,
some people claim it's
not the way one should look at those things. Yeah.
What is the way?
Because they're not just independent factors. In fact, we have developed this theory of information decomposition, which emphasizes the so-called synergistic or complementary information that only comes out if you combine both sources. Yeah. So the gene by itself, the genetic material, the DNA, cannot do much if it is not situated in a complementary environment in which it can develop, and where all the complementary factors that are not internally coded are available. On the other hand, of course, environment cannot do anything without the developing animal or creature with its genetic material. So both need to come together. If you had very flat environment, then genetic information would be useless. If you have a rich environment, if you don't have the building plans or so instructions encoded in the genome, that also would not help.
So that basically means, coming back to this nature of how we think, if we think about the structures that our brain operates with, I was more interested in to which extent those structures are determined by, let's say, biology of our brain, by the way it is wired, let's say, and to which extent is it determined through how we train ourselves to think about the world, this balance?
Yeah, both, but the important point is that we make complementary use of what is in the environment. That is what is called embodied cognition. Yeah. So when we try to follow a ball or so, we don't need to compute its trajectory to see where it lands. We just observe it from point to point and then keep a constant angle towards it. Yeah, because then nature does the computation for us. Nature computes the trajectory of the ball, and so we just need to sample it repeatedly in order to cope with it. And that is also same in biology. So you don't need to encode in your genes how to manufacture a certain vitamin. It just needs to be encoded in your genes in some indirect way how to find some food that contains that vitamin.
Yeah, sure.
That is a complementarity. So you need to have some information about the environment, but at a much more abstract level. You don't need to know the chemical formula of the particular vitamin, neither in your genome nor in your brain. But even though that is necessary for your metabolism, You just need to figure out a way to acquire that. So that is what is important is the control of processes. And for the control of processes, you don't need to know the details of the process itself. You just need to know how to control it.
Like the end game and the way to control it, like where you want to reach, what you want to reach.
For instance,
But
then also how to grow the plants, perhaps that produce the vitamin.
It's like the next level of abstraction, right?
So it gets ever more abstract, and intrinsic and extrinsic get ever more intertwined in a more and more intricate way.
And this is how this complementary information grows, right?
Yes.
The synergistic component.
Yes.
So in which way does it manifest itself in modern, like does it even in any modern algorithmic solutions? Like when we talk about data science, that doesn't seem to be incorporated there.
No, that doesn't seem to incorporate there. But there's, for example, the field of embodied robotics or so, where they develop robots that flexibly use the information provided for free by the environment, or that can easily be extracted from the environment instead of having to compute everything internally.
So one of the examples maybe in deep learning would be reinforcement learning, like this area where they try to have agents that explore the environment, and maybe they do some computational, maybe combination of evolutionary algorithms and reinforcement learning might go in this direction. But why do you think we don't see? So apparently this synergy of external and internal complexity, the synergistic information, was very helpful for us as a species. It's basically our evolutionary bet. This is what we bet our species on, basically. But why do you think it is that we don't see this? It seems to be a very successful bet. Why don't we see that so much around us? The same bet manifesting itself, both on both among biological intelligence, and also why cannot we create systems like this artificially? Why it is so hard to do? It seems like a simple concept, and it seems to be very usable.
Yes.
But why why it is not abundant?
Well, because the symbiosis of the organism and its environment is a very complicated thing. They have co-evolved and they're mutually dependent on each other. And just if you program a computer, it does not have access to the same rich source of information and structure from the environment.
Well, but why don't we see among other species that would be able to have the same way of abstract thinking around us? It seems to be like a very successful evolutionary path. If something is successful in the evolutionary path, it kind of hints that more people, more species would go in this direction. Why don't we see that?
I mean, other species could happily survive without that abstract reasoning by successfully exploiting the irregularities in the environment. So, for example, ants or other social insects are also capable of building up very, very complex structures without any guiding super intelligence behind that, just from local interactions. And of course, if you think about the organization of our brain, there's also nobody in the brain that tells the individual cells that is in charge and tells the individual cells what they should do and what and how they should compute. It just emerges from the interactions between local elements.
Yeah. So did I understand you correctly? Your claim is that we see some systems that are capable of intellectual behavior. They're just not within one organism. Like an ant colony could be seen as a complex system that has some level of intelligence.
Yeah. Okay. Although human societies are so collectively also capable of many things that individuals cannot really achieve.
Okay.
Or the internet is a collective system. It also stores a lot of information, and the information can be used and retrieved, but cannot be so easily localized in any single location.
Yeah, so this about the structures, this is a next kind of direction to discuss, is that it seems that when we talk about social structures, connections, their type and their amount might play a qualitatively important role for the dynamic of the whole structure. And there are a bunch of people who do research on that in this institution and all over the world. Yeah. So and we seem to drastically change that recently, right? So like globally, the number of connections grew. That's for sure.
Yes, of course.
And what could be emergent effects out of this that I don't know, a lot of people say that a lot of bad things happen because of people talk online. Let's say that most of the last 5 years, all I hear is that it's all very bad. It's a lot of control, all these anti-vaxxer stories and so on, all these echo chambers topics. Are there some, or do we even have some results in the direction that kind of highlight some other properties of the system that has more connections other than this echo chamber formation, for example? What are other?
Yeah. Well, first of all, we try to understand the formation and the dynamics of such internet fora, and of course, social aspects, inclusion, exclusion, the confirmation of biases and so on. And it's not something that we are just confronted with. We can understand what is happening to a certain extent, at least scientifically, and it also opens up some new understanding, maybe of the darker sides of the human mind, because people freely expose themselves and they tell things there that they would not tell otherwise.
That's an interesting phenomenon in itself, right? It's you still are present, you still know that you interact with people, but somehow the rules are different.
Yeah, the rules are different, and you don't interact with people face to face.
Yeah. Well, because people care about status a lot, and so evolutionary, probably the attack on the status is a very dangerous thing to do. Yeah. And so the possibility to do it anonymously gives the luxury that people luxury. I'm not sure that this is a good way to characterize it, but probably that's one of the reasons, right? It's just evolutionary, a very, very dangerous act for a monkey to attack another monkey of a higher status.
Of course.
It means a lot of bad things will happen, probably.
Sure. I mean, in the internet, on one hand, have the advantage that you can anonymous, and of course, the other advantage is that nobody can physically retaliate.
That's also true. Yeah. But some of the commands can be brutal. So,
right.
Like, moral pain can be
of course
harder than physical for some people, at least. Yeah. But like coming back to the properties of these connections, because for example, I'm a technopositivist, so I see a lot of positive things about it. Yeah. But and you as the person who is seeing this word of structures, let's say, are there some basic properties of the let's say a graph, or if you use a graph to describe social system, are there some basic structural properties that change if it becomes denser, let's say, because that's what happens. You start to interact with some people that you never would have interacted before, right? So from this perspective, what could be said? Because I'm biased in this. I'm very pro-technology in this sense, and I'd ask you as a less biased person in this direction.
Well,
I'm not sure.
I see many positive aspects of the technology. Of course, the graph in the graph of connections, some restructuring takes place, as you indicate, but it's not necessarily that people have more stable and lasting connections. They have different types of connections, or they connect more easily with people that seem to share the same opinions and the same biases.
Okay.
Yeah.
So it reinforces that.
Yeah, it reinforces things, and there's of course a certain danger there, in particular that it might also lead to social separation, that people no longer talk to each other.
Yeah, there's the very sad book. It's called Bowling Alone. I recommend it if you didn't read it. It's about the guy who studied the statistics of bowling lanes in the US and found out that in the last 20 years, the percentage of lanes on which there was one bowling player drastically increased.
Yeah.
Like 20 years ago, bowling was something where people went together.
Yes, right.
And he's kind of documenting this change of the social fabric.
Of course. So that is a danger that the social interactions with people in the real world are getting fewer, and also you're no longer so easily confronted with different opinions and have to justify or change or adapt your own opinion. You can just selectively use those people that can confirm your opinion. Of course, that is more pleasant.
But you could do it in offline world as well, right?
Like, not so easily. I mean, you interact with your family, with your colleagues or so, and your family you cannot choose. Yeah. Your colleagues you can only choose to a certain extent, very limited extent.
Okay.
Maybe you can choose your wife.
Well, to the best of your capabilities, of course.
Yeah.
Okay. So the point is that since you have to deal with the people that surround you in normal social environment, you have to be more moderate in your judgments and behavior. Yeah, that's understandable.
There are more corrective instances.
Yeah. Okay.
Yeah.
But if
you go extreme or so, you don't find so easily other extremists in your local contacts. But in the internet, that is quite easy.
I also depends on where you go extreme. I'm coming from such a place that it depends. But we also, in some sense, contributing to this because, on the other hand side, the possibility to listen a mathematician talking about mathematical structures for a lot of people before this platform was minuscule.
Yeah.
And a lot of people don't even know what they like. One of the things that I like a lot about podcasts is that surprisingly a lot of people all over the world apparently want to know more than just a soundbite before the commercials.
Yeah.
And this was the major line of thought for 20 years, especially with the rise of TV popularity. People were saying it should be shorter, it should be, I don't know, this should be, something should blow up, otherwise people will not watch. But we see that throughout whatever the culture, whatever the language, the long form conversations are getting eyes. Not maybe, okay, it's not Shakira, but there's surprisingly more people that, like, every time I publish an episode, I'm constantly surprised that more people saw it than I expected would be able to listen to a 1 hour discussion, for example. So this is one of these examples of this constructive bias. We kind of told ourselves a story of how our mind works.
Yeah. But of course, I mean, we have seen such phenomena all over cultural history. Formerly, before writing was invented, people were able to memorize long tales and long episodes and so on. And when writing was invented, there was no need for that any
Plato
longer.
was complaining to that about that to Aristotle, as far as I remember.
Of course, yeah.
He was saying, you with your writing, you destroy wisdom and something like that.
Yeah, but that is not what happened. Yeah,
yes.
I mean, it enhanced our powers that we could do that, and of course we can complain that longer interactions or more intense interactions are reduced, or in TV or in the internet there's a pressure to have shorter and shorter clips, but on the other hand, that enables us to absorb a lot more information in parallel and in a short time. Yeah, I mean, it increases intellectual demands, actually.
Yeah.
Yeah. I mean, maybe we are worried about the quality of the content, but in order to be able to cope with all the influences that you see in competing programs in the internet and within our limited time and in a sequential manner is a high cognitive demand, and it might actually make future generations more intelligent.
Well, and on this note, there's no better way to end this conversation. Thank you very much for finding time. And thank you very much for watching or listening. We publish this podcast everywhere, on YouTube, on all the podcast platforms, Apple Podcasts, Google Podcasts, Spotify, whatever. Please subscribe. Please leave as many stars as you think this podcast is worth. And if you're watching this, you definitely have to like it. Like if you're listening, the stars are optional. If you're watching, the like is you have to do it, because that's the only way you can survive in this business. I'm sorry, guys. Thank you very much, and tune in next time and tell 2 other people if you know somebody who would be interested to listen for an hour. How mathematicians talk about structures. That does get some fire content available for them now.